Hello, I'd like to welcome you to the CERIAS Security Seminar for January 21st. Today it's my honor to introduce Paul Kidwell, who in addition to being a PhD candidate is also a Purdue alumni, having obtained his bachelor's here in 2000. After that he joined the real world for a while before getting a master's at DePaul and then returning here to work on his PhD. He's doing work in analysis of rankings. And today we're going to hear him talk about an algorithm for keystroke detection, showing some of the limits of what we think may be secure, otherwise think would be secure information. So,
thank you.
Paul.
Thank you very much for having me here this afternoon. Recently I've been working with Professor Cleveland, John Girth, and Saptarshi Guha, who's here this afternoon also, on developing a rules-based statistical algorithm for keystroke detection. And so that's what I'll talk a little bit about this afternoon. So what are we getting at here? What are we really trying to do? Well, we are looking for SSH logins, and those SSH logins that we're interested in are those that are interactive sessions where you have a human typing on a keyboard. So what we're looking for are keystrokes, and that's kind of the goal of this algorithm. We want to be able to identify any sort of keystroke packet in an SSH login. And so there's, as far as where this fits into the framework of things, there have been some previous approaches to this where people have looked to classify connections as having keystrokes or not keystrokes. And some of the work that's been done, for instance, Paxson and Zhang took a look at the ratio of small packets to the total number of packets and the interarrival timings with those packets. And they did all right there. And Wegman used a nearest neighbor approach using packet counts, whereas Hernandez Campos used a partitioning and divided each connection up into a sequence of packets. And these packets were there were three modes of activity: bulk, transfer, interactive, and one other, I believe idle was the third category. But the common thread amongst all of these methods for classifying connections that have keystrokes is each one of them used a connection summary type statistics and looked at things that summarize the connection. And where we felt we might be able to do a little better here is we take a more granular approach and looked at the packet level detail and worked from the packet detail upward in order to come up with an alternative method for identifying keystrokes within SSH connections. So what we've got here is a rules-based statistical algorithm. The name comes from the fact that the rules-based portion of it comes from the fact that we use some of the domain knowledge of TCP and SSH and how they behave to construct some rules. Whereas the statistical algorithm portion of the name comes from the fact that we're looking at the distributions of some timings and packet sizes and such. So the goal that we're explicitly trying to get at here is we want to identify packets in any TCP connection that are client keystrokes of an SSH login. So whether this is running on port 20, whether this is a connection using port 22, or whether it's a connection using another port, if there's an SSH if it's an SSH connection, we want to be able to identify the keystrokes there. Our approach to this problem has been a two-pronged approach. The first step was we wanted to develop visualization tools. And these visualization tools should allow us to see keystrokes. We wanted to plot these connections in a way that we got a feeling for what is happening, what characterizes a keystroke, what are the distinctive features. And then we translated those learnings into a algorithm for classifying each packet as a keystroke or not a keystroke. The input to our algorithm here is are the packet arrival times from the network monitor, and also the TCP IP headers from each one of the packets in a connection. The output's going to be, there's two levels of the output here. The first level is each packet in a connection is going to be classified as being a client keystroke packet or not, and the second level of output is going to be at the connection level. each connection will be classified as containing keystrokes or not containing keystrokes. So the properties of this algorithm that make it a nice algorithm here are: one, it's passive. We don't have to inject any packets into the network traffic. Two, we don't employ any knowledge of the packet payload, so we don't look at the payload at all. And three, it seems to be fairly accurate relative to some of the previous work here. So to give you an outline of where we're going today, the first thing we'll do is we will take a brief look at some of the protocol background and how this impacts how we designed our algorithm. The second thing we'll do is we'll take a look at the data sources we used for this project. Third, we'll go through some examples of the visualization tools and look at exactly how we were able to see these keystrokes. The fourth thing we'll do is we'll walk through the algorithm step by step, and finally we'll take a look at the performance here. And feel free as we go through this to ask any questions along the way if there's anything that's not clear or you have any questions. So to get started here, the background protocols. Protocols shape the form of TCP packets. And for the purpose of our discussions here today, we're going to define a keystroke to be the first client data packet sent when a person using SSH presses a key. So that key will generate a sequence of packets as in part because of SSH and in part because of TCP. But that sequence of packets we'll refer to as the keystroke packet sequence. And so for an example here, a standard keystroke packet sequence would begin with a client data packet that contains the data of that particular keystroke. So if you press K, that K will go across to the remote server. In turn, that K has to come back to be displayed on your monitor, so that will again be transferred back as a server data packet and displayed on your monitor. And TCP stipulates that there will be a response, that the reliability mechanism stipulates that there will be an acknowledgement of that data receipt. So a standard keystroke packet sequence will then be a client data packet, a server data packet, followed by a client acknowledgement packet. Additionally, SSH stipulates that all of these data packets have to be of a particular size, or at least all of the client data packets have to be of a particular size. They will be multiples of 4 and between 8 bytes and 252 bytes. And that's due to the encryption there. So as far as this goes, you'll also have some other type of keystroke packet sequences that will arise. And for example, when someone's typing quickly, or perhaps there's a long distance between the server and the client machine, you might have a situation where you have a keystroke packet sequence that consists of a client data packet followed by a server data packet, where that acknowledgement packet is actually lumped onto the following keystrokes initial client data packet. So I think that gives you an idea of the terms that we're working with here as far as what we're looking for and what a keystroke packet sequence is. So the data that we worked with, we used 4 different packet traces here to conduct our development and testing. The first packet trace we used was the Leipzig data set. And what that is, it's a collection of packet trace consisting of a whole lot of connections out of the University of Leipzig back in 2002. We used the second 54 hours of this data set and took all of the SSH connections out of there. So there were 9,077 SSH connections there. And we ended up making a whole lot of plots and using them to develop our visualization tools. We needed a lot of connections of diverse behavior in order to figure out what was characteristic of these SSH connections. So that was primarily of use in our developing visualization tools. The second set of packet traces was built by ourselves using the machines in Purdue Statistics department. So these were manual, what you'd call groundings, things that we knew